Okay, welcome to day 9. We're going to do more work with antiderivatives, also known as the indefinite integral, is what we did on day 8, and something new called the differential equations, which is going to do applications of the antiderivative. So we talked about the antiderivative being the undo of the derivative, and we're always adding a c at the end. When we add a c at the end, it's called the general antiderivative, or the indefinite integral, because I could have any indefinite value for c at the end here, and we're going to work on some more examples. So don't overthink. This is always basically doing these in reverse. So when I do this one, this is going to be, well, x to the first becomes x squared. The reciprocal of that is a half times 5 is 5 over 2 plus 2x. And don't forget your plus c. Best thing about doing the antiderivative, you could always take the derivative to see if what you did is correct. Over here I might have to rewrite some of these. I might have to rewrite this as x to the 1/2, 4x to the negative 2. So when I take the antiderivative, this is x to the 4th. The reciprocal of that, I need a 1/4 up front. Minus, well, let's see. This has to add 1, and top minus bottom is going to be x to the 3/2. And then reciprocal of that is 2/3. And then let's see, I have to add 1 to this, so I'm going to get x to the negative 1. The reciprocal negative 1 is negative 1 times that 4 up front is negative 4. And let's see, I'm going to add 1 to this, so top plus bottom is going to be x to the 8/3. And the reciprocal of that is going to be, not plus, minus 3/8. And don't forget your plus c at the end. Like I said, when you're done, you could take the derivative of all that stuff and you should get what you want. Well, if I go into this, the antiderivative of cosine, based on what we did last class, is sine of x. Don't forget your plus c. And if you put a 5 up front, it's 5 sine of x plus c. Pretty basic, pretty easy. But now we're going to look at maybe those mini chain rules that we did before. How does this 2x affect what we've been doing? Now, I do recall that the argument, the stuff after the trig function, cannot change. So I know this has to be sine of 2x, and don't forget your plus c. But I think I need something up front, because this 2x causes me something later to happen. So I think I need a half up front, because that 2x is going to multiply the derivative by 2 when I did the chain rule. So I need a half up front to get rid of what I wanted. And if I put a 5 in front, it's still going to be sine of 2x, but because of this 5 and this 2, I need a 5 over 2 up front. So basically I'm using that reciprocal of that number in front of x. Same thing here. I know the antiderivative of e to the something has to be e to the same exponent, but what do I need up front here to give me this coefficient of 1 up front? I need a half, just like I did in number 5. And the same thing over here. This would be 5/2 e to the 2x plus c. So I think hopefully you'll notice that this 5 is going along for a free ride, but this extra 2x, these extra 2 x's, is causing a different coefficient to be in front. It's actually we were using the reciprocal. So it's kind of the reverse of that mini chain rule that we've been working on for the last week. So let's go through again what we know and what we think we need to know. If it's just a number like 5, it's going to be that number times x plus c. Again, if it's a power rule, we have to add 1 to that exponent, and then we have to take the reciprocal of that exponent and put it in front, plus c. If there's a coefficient in front, it's just a times that reciprocal, and adding 1 to that exponent plus c. Antiderivative of cosine is sine of x plus c. If there's an a in front, it's just a times sine of x plus c. What if there's a k in front of that x with that argument? Well, I know it still has to be sine of kx plus c, but this k is causing a 1 over k to be in front. And if we have an a and a k, it's a over k sine of kx plus c. That argument after trig cannot change. Well, it'll be consistent for when we do sine. Remember our sine, cosine, negative sine, negative cosine, but the antiderivative is going counterclockwise. These are antis. That's how we got sine. The integral or antiderivative of cosine is sine. Well, let's see. When I do sine, I get negative cosine of x plus c, and a in front gives me negative a times cosine of x plus c. A k here gives me negative cosine of kx plus c, but I need a 1 over k in front, and I have both an a and a k. I get negative a over k cosine of that kx plus c. That argument here of kx cannot change later. That we've established very much with trigonometry. And a couple more here at the end. That antiderivative e to the x is just e to the x plus c. Oh, free ride with that a. Oh, I have a k here, so it's going to be e to the kx because the exponent cannot change on e, but this extra k causes me a 1 over k in front. And if I have an a and a k, it's a over k times e to the exponent of kx plus c. If we do this, I'm going to change it to red. The antiderivative of 1 over x is ln of x plus c. Free ride with that a. And if we really think about this, this is 1 over k times 1 over x. So this is really 1 over k times ln of x. And I have both an a and the k. It is a over k ln of x. Don't forget your plus c. That kx does not cause a kx here. We talked about this before. When we did ln of kx, that kx did not matter. Still, the antiderivative is going to be ln of x. So what is its applications in real life? Well, not real life, at least bigger problems than just plain old math. So f prime is the derivative, and another notation for derivative y prime is dy over dx, also known as the differential. So dy over dx is a differential equation. Is measuring the difference. So how do I undo a dy over dx? I have to use the undo for this is the antiderivative. And the symbol I use for the antiderivative is this integral symbol. That's what we've been working on. So if I have a derivative, and I put an integral sign in front of it, I get my original function. Plus a c. Or I could use this notation. The integral of y prime is going to be y plus c. Or all this other stuff, and I'm getting what I want. So the way I do this, and don't get caught up with this dx at the end when I have an integral sign. This just means with respect to the variable x. That means it's my variable of interest. So if I had to do this example right here, what I do is I bring this over to this side by multiplying it out. So I have dy is equal to x cubed plus 5 dx. To undo the dy, or the derivative of y, I have to do the antiderivative, or the integral sign. What I do to one side, I do to the other side. This is equal to y equals, well, this is going to be x to the 4th, reciprocal 1/4 x to the 4th, plus 5x. And because it's a general solution, I have a plus c at the end. And there we go. If you took this derivative, if you took the dx, or the derivative of this, you would get dy over dx is equal to x to the 3rd plus 5, which is exactly what we had over here in the beginning. That's why the antiderivative is so nice. You can check it at the end. Do you get what you want? Same thing here. I'm going to bring this dt over to the other side. I might rewrite it though. The derivative of w, or dw, is equal to 4 times t to the 1/2 dt. Again, the dt means that I'm using the variable t. I take the integral both sides, I get w is equal to, let's see, I got to add 1 to this, so t to the 1 plus 2 is 3/2. The reciprocal of 3/2 is 2/3 times this 4 that's in front, so I get 8/3 plus c. You can just leave it like that. That is the general solution. I don't know what c is right now. I'll figure it out later if I have to. But then again, I can always take this derivative to see if do I get that? Do I get this when I take the derivative? You should. Okay, next page. Now we're going to do specific, particular solutions. Okay, it's called an initial value problem because you're given some initial value to solve for that c that you had before. So like I said, I could move this dx to the other side, and I could take the antiderivative, or integral, and that becomes y equals, again my variable is x plus antiderivative of sine, cosine of sine of x, plus c. This here means plug in pi, my answer should be 0. If I plug in pi for x, that means this is my x, this is my y. 0 equals pi plus sine of pi plus c. Hopefully you remember sine of pi equals 0, so 0 plus pi, 0 equals pi plus c, or c equals negative pi. So I could take this guy here and rewrite it as y equals x plus sine of x minus pi. And that is my initial value problem. That is the specific equation I have for this given condition of when I use x equals pi, I get y equals 0. And you always could take the derivative of this, and you should better get that. So solving for c is really easy. It's just plugging in an x and a y value. So again, I'm going to move this dx to the other side. I'm going to take the antiderivative. So y equals x squared becomes x to the 3rd. And this is 1/3 times 6 is 2. Plus x becomes x squared. Reciprocal of that is a half times 4 is 2 plus c. That is my general antiderivative, or my general differential equation. I can plug in 2, 10 for the x and the y. 10 equals 2 cubed plus 2 squared plus c. 10 equals 8 plus times 2 is 16 plus 4 times 2 is 8 plus c. 10 equals 24 plus c. c equals negative 14. And therefore I could take this equation, which is the general equation, and rewrite it as y equals 2x cubed plus 2x squared minus 14. That is the specific solution to my initial value problem. Again, I could take that derivative and I would get that as its result. And then finally, wow, this looks like physics to me. Yeah, we're going to be doing physics at some point. I could bring this dt over to the other side. Wow, dt. Maybe my variable is not always x. Maybe it's t for time. Take the antiderivative. My variable is s here, so s equals t squared. Half of that is negative 16 plus 100t plus c. I could plug in those two values. So 50 equals negative 16, 0 squared, plus 100 times 0 plus c. Wow, I love plugging in a 0. Nice number to plug in. So I get 50 is equal to c. So I can rewrite this problem as s equals negative 16t squared plus 100t plus this initial value that I found for c of 50. If you took this derivative, you would get that differential. Okay, thanks for watching the video. Ask questions in class.